Hello, my name is Naeim Mahjouri, and I'm currently a senior at Auburn High School. In this presentation, I'm excited to discuss my research on designing a hybrid 3D printed piezoelectric wheel for energy harvesting and storage in electric vehicles. So, over the past few years, electric vehicles have been on a rapid rise, and this is because traditional combustion engine vehicles release a lot of harmful pollutants into our atmosphere. EVs, on the other hand, rely on more clean and renewable sources. But a major limitation of electric vehicles is that on full charge, they cannot travel great distances, so they must be constantly recharged, and that's both timely and costly. So in order to approach this challenge, different methods have already been implemented, such as photovoltaic cells and electromagnetic induction charging. However, these methods are either very environmentally dependent or extremely expensive. So the ultimate interest is to find a method to continuously harvest energy as the vehicle is in motion to power the batteries without depending on the environment and at a relatively low cost. So after extensive research, I came across a promising solution, the piezoelectric effect. Well, how does this work? Well, certain materials at their atomic level have a lattice structure. Originally, at the center of the structure is a net charge of 0. But if there's compression or tension, now we have a net negative charge and a net positive charge on opposing sides, just like a capacitor. Now, a capacitor stores energy in an electric field, and this piezoelectric material, just like a capacitor, can be used to do work. So the major goal of the study is to find a way to implement these piezoelectric discs into the wheels of an electric vehicle, because as the vehicle is in motion, the ground's going to be exerting a continuous upward force on the wheels. Now, if we put the piezoelectric elements in there, they're going to be deformed by that force from the ground, and this will hopefully produce enough voltage to charge our batteries. Now, here are the major materials I used, and I want to draw your attention to this PZT disc. This is lead zirconate titanate, and this is the piezoelectric material that I used. This is widely commercial and very cheap. I bought a pack of 12 of these for about $4 to $5 on Amazon. Here's some properties of it. The charge constant tells us how much charge is generated per Newton of force. The voltage constant is how much voltage is generated per force. And Curie temperature tells us at what temperature, if we exceed this temperature, will we lose our piezoelectric properties. And this is about 320 degrees Celsius for PZT, and that's way above boiling point. Now, here's how I envision this process to work in the real world. As you can see, this electric vehicle, in the wheels, around the circumference is these gold PZT discs. Now, as it's in motion, you can see that the ground is exerting an upward force, deforming our material, and thus generating voltage to charge our battery. Now, before making my prototype, before running any experiments, I wanted to do the calculations to see if we brought this to the real world. If we had a Tesla, for example, and implemented these piezo discs all around the wheels, how much energy would we generate? And would that be enough to charge the batteries? Well, although the math is extremely important, I'm just going to draw the main points. This formula right here, piezo voltage, is directly proportional to the voltage constant times the stress applied or the force applied times the thickness of our material. And I used these 20 millimeter discs that I purchased off Amazon in these calculations, and I calculated after I found the voltage, the charge, the energy per hour. The energy would be 0.066 kilowatt hours. Now, what does this mean? Is this practical or not? Well, an average Tesla electric car uses about 1 kilowatt hour per 6.5 kilometers. So what we generated would produce, if the vehicle was going at 80 kilometers per hour, we would produce an additional 0.429 kilometers to that 80 kilometers it traveled. So this is like less than half a kilometer for those 80 kilometers. So although it's not practical to charge these high power electric vehicle batteries, it is still viable to charge the low power electronics, such as maybe the car headlights, or maybe electric vehicle sensors, or even electric scooters. Now, as you can see, a typical car headlight uses about 0.06 kilowatt hours of energy, and that's exactly what we produce from those 4 wheels. Now, again, it's crucial to understand that what we're doing is we're converting that wasted frictional energy from the ground in the wheel and converting some of that back into the electric vehicle to be used as work to turn on these headlights. Now, I wanted to see if this math actually makes sense in the real world, so I made my own prototype, and I 3D printed my own wheels. And here's my prototype. As you can see, I have these LED taillights, which represent those headlights. And in the next slide, you can see I brought this prototype back and forth, and there you go. I was able to generate enough energy to turn on those LEDs. And this basically proves that that math was correct in that we were able to generate enough energy to turn on the lights. So before making my prototype, I ran a quick experiment to see if I should connect these piezo discs in either parallel or series. And as you can see, series generates more voltage. Here are the configurations. Next is the speed and force applied versus the output voltage. Force applied is also the weight of the car. As you can see, as both were increased, the output voltage also increased. And here's a quick video of me putting a weight on top of my prototype, putting it on a treadmill and increasing the speed of the treadmill. And as you can see, those LEDs turn on. Now, this is extremely important to see. This is the theoretical versus experimental voltage from that last experiment. As you can see, the theoretical should be linearly increasing. However, our actuals starts to plateau over time. And the limitations here are that not all of the force from the ground is being absorbed by the piezoelectric disc. Some is being absorbed by the tire around it. Also, the faster that the wheel spins, the less time this piezoelectric element has to experience the full force from the ground, thus decreasing the voltage as the speed increases. Now, another fun experiment was the capacitor voltage first time. This is to test the charge storing ability of our prototype. And after 3 minutes, I was able to successfully charge this capacitor to a 5-volt voltage drop. Here are some voltage waveforms I generated. And in conclusion, although we weren't able to generate enough energy to charge these batteries, these high power electronics, we were still able to power these low power electronics, such as the headlights or the LEDs. And again, this demonstrates the viability of piezoelectric materials in the real world to charge electric vehicle headlights. Now, in the future, I hope to determine better materials and also build a better wheel structure in order to maximize the force absorbed by the piezo disc and minimize the force absorbed from the wheel around it. Now, a promising material is this PVDF, which is a flexible piezoelectric material. And as you can see, the properties are about 5 times better than PZT, and it's extremely lightweight, so it won't add any additional mass to the vehicle. Now, I want to say that I conducted all these tests at home. I devised this project myself and had a bunch of fun turning on those LEDs as I made my prototype. And I would also like to thank Ms. Sharman and Ms. Middleton for all their support during this project. Thank you so much for your time.